In this example, we'll be looking at S in the Poynting theorem using a long wire with a steady current I going in it. This wire is not uniform and has a conductivity of sigma, so it acts like a resistor. So our goal here is going to be to find the energy per time going into the wire using the S vector, the Poynting vector, which if you remember is the energy per time crossing an area. And we're going to compare that to the power dissipated in the wire. So the nice thing about this video is that you can pause it at any time, and so I'm going to sometimes suggest that you pause it to try to do the next steps yourself. So right now would probably be a good time to pause and just see how much of this example you can do by yourself without any help from me. And for your future reference, this example is pretty similar to Griffith's example 8.1. Okay, so hopefully you've made some progress on your own and at least thought through some of the steps. So the first step, of course, is if we need to find S, then we need the formula for S, which is E cross B over mu naught. And so that means we first need to figure out E and B in this wire. In fact, both of these are pretty familiar for us, so I'm not necessarily going to recalculate them. The electric field is uniform and constant pointing in the z-hat direction, which we proved in chapter 7 using uniqueness, and we did that thinking about a cylindrical resistor, which is basically what this wire is. Once we have E, that means we also know J using Ohm's law. And now that we have J, we can use Ampere's law to calculate B. If you aren't always successful with Ampere's law and could use more practice, this would be a good time to go through this step on your own. This particular Ampere's law problem we've done a lot is a fat wire with J distributed throughout, so I've done it here on the bottom line, but feel free to stop and go through the algebra yourself, and the answer you get here is this B field. So now we have E and B, so we just need to do E cross B to get what S the Poynting vector is. So go ahead and do that algebra yourself and pay particular attention to which direction your Poynting vector points. So here I've written down the Poynting vector E cross B, it's Z hat cross phi hat, and if you did your cross product carefully, you'll get that that's in minus S hat. So if I do a little more algebra, I get this result, where it's pointing in minus S hat. And if we pause a minute to think what we expect, if power is being dissipated in the wire as heat, then we expect energy to be flowing in to the wire, in through the edge. And indeed, that's what we see, right? If we think about the wire and cross section, the Poynting vector is pointing in minus S hat, it's pointing in, meaning energy is flowing in across the edge of the wire. And then eventually we're going to want to calculate sort of along this edge of the wire, here, how much energy is coming in. So that's at S equals A. So I'm going to rewrite the Poynting vector at that S equals A location. And then we're going to start thinking about the second goal of this question, which is thinking about the balance of the energy flow. All right, so here we have S at A. And now what I want to do next is think about the energy flow in my wire, and I'm just going to now take a chunk of the wire of length L. So that's what I have here, a chunk of the wire of length L, and think about the energy being dissipated in that chunk and the energy flowing in through that chunk. And Poynting theorem tells us that the change in time of the energy inside the wire, both in terms of mechanical energy W and energy stored in the field, the change in time of that energy has to be equal to the energy flowing in or out through the boundary. And here this is set up as the energy flowing out. And then if I include the appropriate minus sign, it's actually energy flowing in. So a positive change in time of the energy inside the volume must result because energy has flowed in through the boundaries. All right, so now we're equipped to calculate the S dot dA for this little chunk of wire that I have right here. But we also want to be able to calculate this side. And to do that, we need to know how UEM, the energy stored in the fields, is changing, and how W, the work done on the wire, is changing. So this one's pretty easy. UEM is, if you remember, proportional to E squared plus B squared. And if we take the time derivative, that means we only get a change of this UEM if the E and B fields are changing, and they're not in this situation. All right. So we just decided that UEM is 0, so that means our next task is to figure out ddt of W. So this would be a good place to pause and see if you can think of what that means physically and if we know any equations to find that. And then once we found that, the next thing we'll do is figure out this S dot dA over the surface coming into the wire. But first, take a moment to figure out if you know what this means. All right, so on this new page, I've redrawn our diagram, and then with UEM0, we just have whatever dW dt is, the change in that energy is whatever is flowing in. And here in the case of the wire, the physical interpretation of this is the power dissipated in the wire, right? Energy is flowing in. The Poynting vector tells us how the energy is flowing in the sides here of the wire, here and here, flowing into the wire. And then dW dt is the power dissipated in the wire. Okay, so we have an equation for power dissipated, right? This is back from physics, intro physics, right? The power dissipated is P equals IV. Okay, so this is a good time to figure out I and V on your own. So pause for a second and do that, and I'll also write them out for you in the next second. So the current, since it is flowing uniformly throughout the wire, is just J times the cross-sectional area of the wire. J we already know is sigma E naught, and the cross-sectional area of the wire is pi A squared. So that's how I got this equation here. And then V, we actually know that back from the chapter 7 derivation, but we know V is changing uniformly along the wire, so delta V always equals minus the integral of E dot dl. But in this case, that just turns out to simply give us E naught times L. All right, and so you can go back to chapter 7 where we derived the resistance of the wire and the E field in the wire, and we also did that at that point. Okay, so now we have I and we have delta V, so we can get P. All right, and there it is. So you can also pause and go through the algebra right now if you'd like. Okay, so now what we have is we've computed this left-hand side and we have S, but we need to compute this side, so we need to do S dot dA over a closed surface that's enclosing this wire here. So it'll be the closed cylindrical surface right here at the edge, extending here, here, and here. All right. Think for a minute which parts, like is it these two end caps or is it the curvy part here, contribute to that integral. I've rewritten the Poynting vector here, and the key thing to note is that it points in S hat, minus S hat, and so it's going to be the integral on the curvy side of the cylinder, S dot dA, that it'll tell us about the energy flowing in per time. So go ahead and compute that integral, S dot A, over that curvy part to figure out the energy going in per time. And according to Poynting's theorem, it should equal this that we just calculated here, as long as we believe in energy conservation. All right, I'm going to do the integral out for you here. So this is the one of the curved side. And if we look at the equation, we've already set it up to be on the curved side at S equals A. And so S is a constant there. So we really just need to take the dot product of S hat with dA. They point in the same direction. The fact that the Poynting vector is pointing inward is already captured by this minus sign. So then it's really just the magnitude of, it's really just S times the area of the curved side. So that is 2 pi A times L. And then S we already have, so if we just take a second to put those together. All right, when I put them together, I get this that I've just written, which makes me realize that I made a mistake right here when I copied it over. That shouldn't have been a squared, so let me erase that. Oh, I erased a lot. Okay, so I paused it, I fixed that. And if you notice, the key thing here is that we've got the same answer, right? So our power dissipated as heat in the resistor is the same as the energy per time coming in. And this is energy per time flowing in through the fields across the sides of the resistor. All right, so this is good. Energy conservation works, and we've also gotten a good example on how to use the Poynting vector.